All right, welcome back to physics. So let's take a look at a couple of these problems that are posted. These are FRQ questions that are from Unit 7. These are on rotation. So notice rotation also includes torque. Okay, let's take a look at the first problem. So the first problem has this pivot with a bar hanging on it. And then there's three different places that we could hang this. So an important thing here. So this is getting at the torque that's coming from something. So let's take a look. That's an important thing to think about. Is that on my bar here, my bar is generating some torque. So I have a pivot point. This bar is generating torque. So what I want to do is I want to simplify this and pretend, well, let's pretend all of the mass is at the center of mass for this bar. Should work okay. Right? It's a consistent bar, so it's easy to figure out where the center of mass is likely to be. So I'm going to figure that this force is going to provide the torque coming from this bar. So I can figure out how much torque is coming from this bar. It needs to be counteracted by using my torque equation, which is going to be my force times the lever arm that's perpendicular to that. So we had a longer equation for this, so FR sine theta is a way to take that into account, but I need to have a force perpendicular to my lever arm. Right? So we're in pretty good shape here, right? So I've got a force that is going to be mg, and I've got some lever arm here that's going to be constant. This is a statics problem, right? So statics are handy because it means it's not moving. So the question is asking us, what are they asking us? Rank the hook locations according to the amount of tension sports they would experience. So they're asking tension. So they're asking what's going to have the most amount of force and what's the least amount of force. So if I connect something here, here, or here, right? So this is their position A, B, and C. So if I connect something at these different locations, what's the torque going to be? Well, let's see. So this is static, so it means that the sum of my, so it's not going anywhere. So we can think of this in terms of Newton's third law of rotation. So instead of saying acceleration is equal to the sum of the forces over the mass, Newton's third law of rotation is going to say angular acceleration is equal to not the sum of the forces, but the sum of the torques, and not over mass, but over the moment of inertia. Right? Well, don't worry, this is going to simplify, right? So if this is 0, I can get rid of this. So this means the sum of my torques needs to add up to 0. So that means that this one, right, which is going in a clockwise direction, is going to be counteracted by one of these three. So that means that this one, so the force of my mg times my lever arm, which I was calling R here, is going to be going in clockwise direction. So I'll make this negative, and I'm going to add together some of the other force, and call this force of A times whatever lever arm it has, which is going to be something smaller. So I'll call this R sub A. So you can rationalize how this is going to work, right? So and if R is identical, so if my distance, if I was to put this position directly above the center of mass, right, my distance would be identical and my forces would be identical. And hopefully that makes sense, right? So that means you're just balancing this, that you're just taking this bar and you're balancing it right at the center point. There's really no effect of having this axis of rotation. If I'm pulling at point C, right, I have a longer radius. So I have a longer distance, so I need less force. Hopefully this makes sense to you, right? So and if I was at A, I have a shorter radius here, and I need a larger force. Right? So I have to counteract this. This is not changing. This is constant. So I need to counteract that. So that means larger radius means smaller force. So I'm going to rank these. So the further away it is, the less force is going to be required to maintain this in static equilibrium. So C is going to be greatest, which followed by B, sorry, C is going to be least, C is going to be the least amount of force, followed by B, followed by A. So the force is going to follow this one. So looking for a justification for this. So what they're looking for you to identify is that you recognize torque is going to be force times lever arm. So you want to have something in your explanation that says torque is force times lever arm. Let's go on to the next one. Part B. Oh, nice. So now we're going to hang the sign with the cable. And the cable breaks, and the sign starts rotating clockwise. So 3 different times. I've time at 1, time at 2, time at 3. Right. So this is something that's now rotating and accelerating, but it's kind of tricky because a couple of things going on. Right. So let's see. So the angular acceleration. What's causing this to have angular acceleration? Well, think about this, right? So at position T1, so here's my bar, right? And I'm going to pretend all of the mass is at the center of mass, and it's experienced a force of gravity pulling it straight down. So that's the only force that's acting on this, right? So, and that force of gravity is pulling it straight down. When I get to my lower position, has gravity changed? No. I still have the same force of gravity, but what is different is the direction that's perpendicular to the lever arm, right? So here I have most of my force is going perpendicular to my lever arm, so my torque, that force that is perpendicular to the lever arm, most of that mg is going to generate torque. Here I have just a small component that's perpendicular, so there's less of that force that's going into this. But so the first thing to recognize is that torque's going to be a little bit less as it falls, and when it gets to be perfectly vertical, right? So when my bar now is just past what they call T3 here, my bar is perfectly vertical, right? mg is pulling straight down. There is no torque, right? So my angular acceleration is going to be 0. So what are the question they're asking us? They're asking us, indicate at which times, if any, the angular acceleration of the sign, the thing falling, is greatest, right? So I'm thinking here, right, this is equal to, torque is equal to I alpha, right, as Newton's second law of rotation. So moment of inertia is not changing, and my bar is maintaining the same site. So I'm going to have more torque and more angular acceleration when I'm more horizontal. So I become more vertical, it's going to be less. And what they're looking for you to recognize here in the explanation is that the torque comes from the amount of force that's perpendicular to the lever arm, and that will decrease as the object falls to become vertical. So we need to get that into your explanation. Part 2, show that alpha can be modeled. So angular acceleration can be modeled with this thing. Whew. The rotational inertia of the sign is 1/3 ml squared. Okay, super. So math, right? So now we're just going to go through, and they've given us the answer. So we're gonna figure this out. Right? So what I'm going to do, I'm going to use this equation. It says that sum of the torques, there's only one, must be equal to I alpha. So if you like, we can back all the way up to Newton's third law for rotation. So acceleration, angular acceleration is going to be the sum of the torques divided by the moment of inertia. Right? Well, this is asking what they're asking us to get to angular acceleration. So sum of my torques, I only have one. Right? I'm going to be careful though. Right? So they allow me to use theta here. So I'm going to think about it this way. I'm going to have some force. Right? Some of that's going to be perpendicular, and I want to find that component of it. Right? So they're telling me. So tell me the sine of the angle. This is the angle they're giving me in here. Action of the torque. Right? It's going to be the force that's perpendicular to the lever arm. What's my lever arm? My lever arm in this case is going to be 1/2 my length. Right? So that force, I'm going to pretend all the force is acting right at the center of it. Right? I'm divided by the moment of inertia. They tell me the moment of inertia for this is 1/3 mass times the lever arm squared. So the only thing I have to deal with is this perpendicular sign. Right? And they're telling me the answer to this, so I'm just going to plug it in. They're telling me hey, force is going to be 1/2 L times the sine of theta. and divide this by 1/3 ml squared. And now I'm going to rearrange this and trust that I'll come up with the equation they ended up with. So I divide by a fraction. It's the same as multiplying by the inverse. So I'll end up with 3/4. One of my L's will cancel. Sine theta over 2 ml naught squared. And that's where we're going. So a couple of important things here. So one, I have to use the center of mass as my point, my axis of rotation, my axis, but I have to use the center of mass as the point at which the forces are being applied. So I'll use 1/2 L, and I'll have to take into account that fraction that's perpendicular as it changes. Part C. Part C, student wants to describe the angular velocity of the sign as it rotates to propose the following equation. Does this make physical sense? Well, let's see what the equation is. So the equation is 3g sine theta, right? So what they're looking for you to do is to recognize that this is the same equation, right? And they just multiply this by time, right? So I'll have 3, the force, or not the force, maybe I need to change this to mg to get to their final answer. Did I skip the mg part of it? Maybe I did. So this is equal to 3g sine theta over 2L. And what they do for this next question is they just multiply all that times time. Does that make sense? Right? Well, I'm going to think about this. If I took, if I want to get to velocity, could I multiply acceleration times time? Would they get me velocity? Well, yeah, it should work, right? So, and so what they're looking for you to recognize is that even though this has a lot of variables in here, that I can still describe velocity and angular velocity, right? So my velocity is acceleration times my angular velocity is going to be angular acceleration times time. That's a way to describe it, sure. So is it legitimate to describe it this way? Well, yes, because this is a valid equation. And if you want to, you can refer back to the formula sheet, which has something like this, right? So if I multiply acceleration times time, that would tell me final velocity, or the change in velocity, and omega. Next question says students attach a rotary motion sensor to the sign, and they record omega, and they create a graph of this. Well, one way I can get there is try to work out units. Right? So I need my units to end up as 1/seconds for omega. So let's see if this works out. So I want to take the first one. They're telling me this is root 3g cosine theta over L. Well, let's try some process of elimination. So I'm going to look at this. I'm going to say, well, I've got 3g cosine theta. This is the first. So the units work out. Well, what's my unit for g? It's going to be meters per second squared. Right? And my units for L, my length is going to be in meters, and I'm going to take the square root of this. Right? So meters will cancel, and I'm left with the root of 1/second squared, or root of 1 over. Take the root of that, I get 1/second. So the units for the first one works out. Let's check the units for the second one. So it's telling me root 3L cosine theta over G. This can't work out because it's the opposite of that, right? So I'm going to end up with meters divided by meters per second squared. Take the root of that, right? I'm going to simplify this, right? So I'm going to multiply my numerator by the inverse of my denominator, right? So this is going to be root meters times second squared per meter, and I get seconds as the unit, and that's not right for omega, so it can't be that one. Check the units for this one. So I have 3g sine theta over L. And what's this going to give me? This is going to give me, this is going to be the same as the first one, right? So I'll end up with the correct units. And then the last one is going to be the same as the second one. So I'm going to end up with incorrect units. So I know this is a possibility and the third one's a possibility. So the only difference between those is a sine and cosine. Well, there I have to think about this, right? So when I release something from rest, what's the initial angular velocity, right? And this is what they're showing here. They're showing here I'm releasing something from rest, right? So at 0 degrees, I have 6 rads. So at 90 degrees, I have 0. So what I want is I want a function that at 90 degrees gives me 0. And that's going to have to be the cosine function, right? So cosine of 90 is going to give me 0. So these are two things to look for you to recognize that it needs to start from 0. So the best match for this is going to be cosine, and you need to end up with the correct units. So the cosine function that has g on the top is the one that's going to work the best. Again, features of the graph. So they're looking for you to recognize at 90 degrees this is 0 and make that work. Okay, let me stop here for this one. Okay, welcome back to physics. So this is the second question of the free response questions that are in rotation. The first one was on torque. This one, more classic rotation problem. So a couple of really important things to get across and for you to make sure that you can relay to the College Board on this one. So first one, so let's see what I'm doing. Wrong grade. So I'm here, I'm looking at something that's on a ramp and is going to roll. So the things I want to be thinking about is that I'm going to have both angular velocity and linear velocity. So I'm going to have two things going on here, and likely I'm going to have to separate these two. I don't know. We'll see where it goes. So they're giving me something. They're telling me it has a moment of inertia of I. Fine. It has some mass. It's fine. It's placed some height. Fine. And they want me first to draw arrows to reflect the magnitude of forces and diagram. Okay. Here we go. So I'm going to have this this thing that's going down the hill. So I'm going to think about what is it touching, and what is it what's interacting with it at a distance. So it's touching the surface here. So when anything's touching, I'm going to have from that point, I'm going to have some normal force coming from that. I'm going to have some center of mass, right? So notice the center of mass for this object is a place where there is no mass. So right in the middle, I'm going to have my center of mass, but that's fine. I'm going to draw my gravity coming from that. And I'm going to be a little bit careful there. So I'm trying to make that force of gravity be longer than my normal force, right? So force of gravity is doing two things. It's pulling it into the board and it's pulling it down. So I'm going to make sure force of gravity is longer than my normal force in this case. And lastly, this is not sliding, it's rolling. So something must be causing it to roll. And so there must be some torque coming, or some force coming. And in this case, it's coming from friction. I'm going to make that a smaller force. I'm going to have a force of friction that's pushing it backwards. Quick question. So is it static or kinetic friction? Remember, kinetic friction is when things are moving. And static friction is when things are stationary. Technically, this is rolling without slipping. So as it rolls, it touches right at this point and it does not slide. So this is static friction that's causing this. Remember, static friction can be up to a certain maximum. Kinetic friction is always going to be the same value. So I want to be careful about this. So when I have something that's rolling without slipping, that I'm going to have static friction that's providing that torque to allow it to rotate. And this is why wheels are very efficient, because it takes a small amount of friction to get something to rotate, right? All you're doing is getting it to rotate. You're not trying to overcome anything else, and you don't lose as much as if you're like dragging it across the floor. So 3 forces on this, and I'm sure they give you 1 point for each of those 3 forces. And take off a point if you get any rocks. So they're going to give you a second thing, right? So this is a hoop. They're giving you, now they're going to give you a disc, and I'm going to tell you that the moment of inertia of the disc is greater than the moment of inertia of the hoop. Huh. moment of inertia of the disk is greater than moment of inertia of the hoop. Well, let me think about this one for just a minute. So it seems unusual to me. So let's see. So if you recall from our class, a disk had a moment of inertia of 1/2 mr squared. Moment of inertia of a hoop was mr squared. And they're telling me that this is greater than this. Interesting. So it's they're throwing you a little bit of a curveball here. So anyway, I'm going to have this moment of inertia. So notice that my moment of inertia can come from two things. I could have more mass, or I could have more radius. So they're telling me the mass is the same. So it's the same mass as the other one. So m0. So these two masses are the same. So my two radii must be different enough to make this be true. Here's the key thing that they're working off of, right? So, and I'll show you. I'll describe the point distribution on this. So, key things that they're working on. So I have two things that are starting up here. It doesn't matter if it's a hoop, a disc, whatever. The amount of energy that this starts with, right? That's coming from gravitational potential energy. Here close to the surface of the Earth, that's going to be mgh. They have the same mass and the same height, so they're starting with the same potential energy. So that's one thing that you want to say. One, same potential energy for a disk is going to be equal to the potential energy for the hoop. Use words for that, not equations. Second thing, some of that energy is going to get converted into rotational kinetic energy. So when you get down here at this point, right, I'm going to have linear velocity, so I'm going to have some linear kinetic energy, but I'm also going to have some rotational kinetic energy. And that thing that has more mass distributed further away is going to take more energy, right, to get it to rotate. Right? So, I'm going to say that thing that has larger moment of inertia, right, that means there's more mass distributed further away. So a larger moment of inertia is going to have more rotational kinetic energy, right? So it's going to be going slower, right? So larger moment of inertia means lower velocity, linear velocity, right? So a thing that has the larger moment of inertia. Certainly they threw us a curveball here because the thing that we usually think of, we think of these, if they had the same radius, right, they would have the moment of inertia would be like this, but they're throwing me a curveball saying this disk, right, must be really big, right? So it's much wider, so you're going to have more mass further away. And so it's going to, so my disk is going to take more energy to get it to rotate than my hoop. My hoop's going to get to the bottom. So that's the second thing I want you to recognize. I want you to recognize that that thing, what do they say? The disk has a larger moment of inertia, so it's going to have a lower velocity. But now we're at a cliff, so we're going to forget about everything else. So these things have two different vertical velocities, but they're the same height, right? So now I'm at a cliff, right? And for a cliff, it doesn't matter how fast you're going horizontally. What matters is your vertical velocity. So the time to land doesn't depend upon vertical velocity. So what they're looking for you to identify is that time to landing is the same. But lastly, there is a difference. So if you have more vertical velocity, right, you'll go further before you land. All right, so the one that's going to go further out is going to be the thing that has larger vertical velocity. So the thing that has the smaller moment of inertia. So the hoop will go further. And looking for you to say those things in some sort of coherent way without saying too many other things that don't make sense. Here's the point breakdown. So you get 1 point earned. Let me put it into the field of view here. So 1 point earned for saying the hoop and the disk have the same initial gravitational potential energy. 1 point is earned for either stating the following kinetic energy. So the disk is going to have greater rotational kinetic energy. And then 1 point for stating both obviously takes the same amount of time, and 1 point for stating that the hoop's going to travel further, and then 1 point for stating it well enough. This last point is usually pretty easy to get, so don't stress about getting all of your verb tenses correct and complete sentences. If you can relate it in a reasonable way that makes sense, that you'll get credit for it. Anyway, hope that's helped. That's the second of the rotation problems. Hope to talk to you soon. Bye.